I made it. I am in Roswell, New Mexico. Beth is going to be so happy. I wonder where she is. Better call her. Hey, Beth.
Hey, Marty. Where are you? I'm getting ready for the show.
I'm in Roswell, New Mexico. You know, the show's all about landing on other planets.
You're in Roswell, New Mexico? The show isn't about aliens landing on this planet. It's about us landing on other planets and why it's so hard.
Well, let me tell you, it is really flat here. I mean, it would be easy to land something, if you know what I mean.
That was a weather balloon 70 years ago.
Oh, it wasn't a UFO with little green men?
No, now can you get back here so we can start the show?
Yeah, it's going to take me some time.
It better be soon, because this is STEM in 30.
I'd better get back to DC. Hi, I'm Marty.
And I'm Beth, and we are coming to you live from the Stephen F. Udvar-Hazy Center in Chantilly, Virginia.
We're standing in front of Space Shuttle Discovery. This thing spent 365 days in space over the course of 39 missions. It flew over 148 million miles.
Now, today's show is about landing on other planets, and there's some big misconceptions about the space shuttle. They were never built to land on other planets. In fact, the only planet that this ever landed on was here on Earth.
The space shuttle flew in low Earth orbit, which basically means it circled the Earth. And I'm guessing that our friends from Jefferson Academy already know that. They're here today. They've got some really great questions that they are ready to ask our expert.
Now, if you're watching us on television or online, remember you can participate too in our discussion. You can submit a question in the little box to the right on your screen. We may take it live here on the air, or if not, we do have an expert standing by to answer it.
Landing on other planets is hard, and some of our friends from Jefferson Academy are trying their hand today at creating simulated Martian landers. And what their job today is to do is to take an extronaut and try to get it to land safely here on the floor. And let me tell you, they have been working extremely hard on this challenge. I cannot wait to see how they do.
You gonna make me say it?
Yeah, otherwise I'm gonna egg you on.
Okay, no more yokes. Now, Marty, you actually spent some time in Roswell, New Mexico, but you were not looking for aliens.
I was not. Robert Goddard spent a lot of time in Roswell, New Mexico, building and launching rockets. And I got an opportunity to go to the Roswell Museum and Art Center, where they have recreated his lab with a lot of the original equipment. It is almost exactly like it was back then.
I'm sure you were very excited. Now, Robert Goddard is known as the father of modern rocketry. He was credited as being the first person to use liquid fuel in a rocket. So, let's go check it out.
I'm now joined by Bill Siders, docent and member of the Board of Trustees at the Roswell Museum and Art Center. Bill, thanks so much for talking with us.
You're welcome.
Now, we are in a recreation of Robert Goddard's lab. Tell us a little bit about Robert Goddard.
Robert Goddard is a very unusual man, born in 1882. So he came of age at the turn of the century. He wrote the definitive papers on rockets and rocket launching in the teens, 1914, 1916. He did the technology, the science work. And as you see around us here, he applied the technology to the problems in rockets. He was an engineer. I mean, he designed this. This rocket sitting here was a rocket that was built by him and his staff. You couldn't buy anything. He did the whole thing. He was an engineer, a technologist, and a scientist. That's a nice acronym, STEM.
Now, why did Robert Goddard choose Roswell?
Because of a friend. He had a friend, Charles Lindbergh, and they used to get together on a regular basis. They would get out on Goddard's back porch and talk over what was going on.
I can only imagine what those conversations were like.
Well, one of them occurred when Goddard had had an explosion with his rockets in Massachusetts. So they packed all of this stuff up, all of the equipment, put it on a train, shipped it out to Roswell, New Mexico.
And started launching rockets from here.
And launched rockets. He set up a test stand not more than about 3 miles from where we are right here, tested all of his rocket designs and engine designs through the 1930s. And they went to a ranch and they launched their rockets out there.
And that really was a precursor for all of the rockets that we have today, right?
When he started working with rockets, the old rockets that have been around, you know, the sky rockets we see at the 4th of July, they have an efficiency of about 6%. 6% of the energy generated goes into kinetic energy to make it go. Goddard, after a few years of research, had improved that to 60%. Every rocket that goes up today is a Goddard rocket.
Wow, from this angle, you really get an idea of the scale and just how immense the space shuttle is. Now today I'm joined by Dr. Ian Clark, the principal investigator for the low-density supersonic decelerators at NASA's Jet Propulsion Laboratory. Thank you so much for joining us today.
Thanks for having me. It's awesome to be here.
That title is a mouthful.
It's a lot of syllables.
Now, we've been landing on Mars for a long time, and we've done it a lot of different ways. Can you kind of talk us through that?
Sure. Let me first talk about how landing on Mars is so incredibly difficult and why it's difficult. Let's use Curiosity, a recent example. We landed Curiosity rover on the surface of Mars a few years ago. When it started at the top of the atmosphere, it was going 13,500 miles an hour. It had an enormous amount of energy in it, generally in the form of kinetic energy, energy of moving bodies. Its combination of kinetic energy and potential energy was 60 billion joules, which is enough energy to power a standard light bulb about 35 years, or an entire house for a year and a half. But Curiosity had to take all of that energy and get rid of it in 7 minutes. And it had to do it safely without damaging the spacecraft. So we've been doing this for 40 years, going back to when we first landed on the surface of Mars with the twin Viking landers. And the techniques have been similar, but we've made improvements. Viking, back in 1976, started at the top of the atmosphere with an enormous aeroshell. And it was shaped to create a lot of atmospheric drag to help slow from 13,000 miles an hour down to about 1,000 miles an hour. But that's all the deceleration that aeroshell could provide. But it still removed 99.5% of that initial energy. There's still 0.5% left, and you're going 1,000 miles an hour. So what did it do? It had to slam on the emergency brake, and it deployed a large 65-foot diameter parachute at twice the speed of sound. That parachute helped slow Viking down from 1,000 miles an hour to about 200 miles an hour. So it's gotten rid of 99.98% of all of that initial energy, but it still has that 0.02% left, and it's going 200 miles an hour, which is still pretty fast, right? Not very comfortable landing. So Viking then had to turn on its rocket engines, and it used rocket engines to slow it from 200 miles an hour to 0 miles an hour and put it safely on the surface where it landed. Since Viking, we've made some improvements. We've got materials now that are more capable of withstanding the heating environment that you have, the extreme heating environment when you enter an atmosphere like Mars. We've got techniques for flying these very blunt objects through the atmosphere to improve our landing capability and be able to slow down higher in the atmosphere. We've also improved on our landing systems. We've gone from using just basic rocket engines like what Viking did to new innovative techniques like using airbags, like the giant airbags behind me that were used or tested to help land the Spirit and Opportunity rovers. And more recently, we used the sky crane system on Curiosity, this spider-like contraption to slow the rover down and gently put it on the surface, where it is today doing amazing science for us.
That doesn't sound very easy.
Oh, it's tremendously difficult. So many things have to happen just right and in a very short amount of time.
Wow. Now, engineering for landing a robot or a rover on Mars is one thing, but designing something for humans to come back seems like it's even more challenging.
Oh, I mean, when you talk about the scales and the energies associated with that, yes, they can be orders of magnitude more difficult.
Wow. Now, astronauts came back on the space shuttle that you see behind us, but the astronauts that come back from the International Space Station today come back in a capsule called the Soyuz, and it lands a little bit differently. Beth had an opportunity to talk to a couple of astronauts that actually landed in a Soyuz. Check this out.
I'm here with Paolo Nespoli, who is an Italian astronaut with the European Space Agency. Thank you so much for coming and talking to us today at STEM in 30.
Thank you for inviting me here. It's a pleasure.
Now, you flew both on the shuttle and on the Soyuz.
Yes.
Can you explain the difference between the two spacecraft?
The re-entry is completely different. The Soyuz re-enters with a parachute. It's pretty much fairly rough, I would say. I usually summarize it, say that it's a sequence of catastrophic events that happen in rapid succession until you eventually go to the last part, which is the soft landing, which is equivalent to a car crash between a truck and a car. And you know, you are in a car, not in a truck. And then you are on Earth, like, whoa, that was pretty good entry.
Now we are joined by Tim Kopra. Thank you so much for being here today.
It's my pleasure.
You were on the space shuttle and the Soyuz.
Right.
You want to tell us how landing in those two were?
You know, landing actually is the biggest difference. When you land with a space shuttle, it lands on a runway, and it's very similar to an airplane. But when you come home on a Soyuz, it lands underneath a parachute. When you come down, you get thrown around quite a bit, and then before landing, some jets fire to soften the blow, but it is a very firm hit on the ground.
How do you think future missions to Mars, there's no water down there, there's no runway, how are we going to land on that planet?
You know, we're going to have to be very careful, right? We need to figure out the right way to get the crew down safely. In all likelihood, it'll be something similar to what some companies are doing now. We have some sort of thrust that allows us to land softer, and that's one viable way to get down on the planet.
What about the big airbags? Do you think you guys would want to take a tumble down?
You know, I think that's probably not a great idea. You know, one of the reasons it's not a great idea is because it's going to take us a long time to get to Mars, and we'll be deconditioned. And so you really don't want to perturb your body any more than you have to.
So you really want a smooth landing?
That would be perfect. Yeah, if we can do that, that would be great.
Thank you so much for joining us.
My pleasure.
These guys look like they're doing an exceptional job. Ian, do you have any advice for them as they build their landers?
It looks like they're doing great work. You know, one of the tricks that we've learned, it's so easy to think about all the things that could go wrong and have to try to make sure that they don't happen. A lot of times it's better and easier to think about all the things that have to happen just right and make sure that those do happen the way they need to happen.
Awesome. Well, they've got a little bit of extra time to work on that. And while they're working, tell us about the low-density supersonic decelerators.
So LDSD, or the Low Density Supersonic Accelerators, is a project aimed at developing new technologies for future Mars missions. When we landed Curiosity a few years ago, it's a 1-ton rover the size of a car, and it was just a tremendous engineering undertaking. It was the largest, most massive thing we had ever landed on another planet. And in the process of developing the system to land it, we started realizing that if we wanted to land bigger payloads, and we do, you know, thinking about into the horizon, the just breadth of exciting science missions. We want to be able to return samples from Mars and bring them back to Earth so we can study them in more detail. And of course, recently the President reiterated our commitment to putting humans on the surface of Mars. So to do that, we needed new technologies, new capabilities to land those very, very massive payloads on the surface of Mars. Curiosity was a ton. In order to put humans on the surface of Mars, you're going to have to figure out to go from 1 ton to 2 tons to 5 to tens of tons, maybe even 100 tons on the surface of Mars.
So what exactly does the decelerator do? It's not a parachute.
Well, it's a combination of parachutes, right? When we have to land on Mars, we have to pull out all the stops, literally. We have inflatable drag devices that are deployed in a fraction of a second and grow the size of the aeroshell to make it bigger, to allow it to create more drag, to slow it down in the atmosphere. But we also have to couple those with other technologies like parachutes. So we've been developing a parachute, an enormous 100-foot diameter parachute that would generate 2.5 times the drag of any parachute used previously, and has to be able to survive at twice the speed of sound. Basically, how do you take 200 pounds of nylon and Kevlar and get it to inflate successfully in a 2,000-mile-an-hour wind?
And I'm guessing all of those tests went perfectly the first time.
Oh, never. You know, one of the reasons why we do the tests is to see what happens, right? If we knew the answers ahead of time, we probably wouldn't need to do the test to begin with. But we do the tests to learn and to see new things, and we had a tremendous amount of that.
Awesome. You ready to take some questions?
Absolutely.
All right, let's start with an online question. What kinds of materials are used to build the supersonic parachutes?
Great question. Most of the materials are relatively common materials, things like nylon or polyester. Same kind of nylon that maybe your camping tent is made out of. But we couple those very lightweight and relatively strong materials with significantly stronger materials like Kevlar. Same kind of Kevlar that we use to build bulletproof vests out of, for example.
Okay. All right, let's go to an audience question.
How did a spacecraft slow down when landing on a planet?
How do spacecraft slow down when they land on other planets? A variety of techniques. The dominant mechanism is we use drag. If there's an atmosphere to work with, we try to use that atmosphere to create drag to help slow us down. So Viking, for example, had to go from 10,000 miles an hour down to 1,000 miles an hour, predominantly using drag, and then from 1,000 miles an hour to 200 miles an hour, again using drag from a parachute. And then ultimately, we had to take that last little bit out using rocket fuel.
What's the difference between the two atmospheres here on Earth and on Mars?
Great question. Here on Earth, the atmosphere, though it doesn't seem like it to us, is really thick. It's this nice thick soup, which means that to generate drag, it's relatively easy. I don't have to have something too large. But at Mars, the atmosphere is extremely thin. It's about 1% the thickness of Earth's atmosphere. So things need to be 10 times bigger at Mars than they would be at Earth. The Viking aeroshell, for example, was about 10 feet in diameter. The Curiosity aeroshell was 15 feet in diameter. And the parachute for Curiosity was 70 feet in diameter. Just enormous devices.
Wow. All right, let's go to an online question. How long does it take to build a Mars rover?
Years. You know, the design of the Mars rovers can take years and years, and then actually fabricating, putting all the pieces together, and then testing the rover, making sure it's going to do the job that it needs to do, may take years as well. So for example, it's 2016. We've been working for a few years now on a Mars 2020 rover that will launch in, surprise, 2020.
Well, recently there was an announcement by SpaceX about sending humans to Mars in the future. Check this out.
SpaceX is a major innovator in the commercial space industry. They currently partner with NASA to provide resupply missions to the International Space Station. They have achieved a major milestone in rocketry. They have successfully landed a rocket vertically, which allows for rapid reuse. This makes human spaceflight much cheaper and much more efficient. Elon Musk, their founder, has a vision for colonizing Mars. They want to create a rocket-type spaceship that can accommodate 100 passengers that will travel to Mars in as little as 3 months. Once there, their rocket will land vertically, which allows humans to leave Mars, if they ever need to. They hope to achieve this in your lifetime. Do you want to live on Mars?
Okay, so Ian, are you ready to test some of these contraptions?
Oh, I'm excited.
All right,
Excited.
Okay, don't start. You'll get Marty started. All right, do you guys want to tell us what was your thought process in developing this?
Our thought process in developing this was we wanted this to be a parachute, but it came out different, and we didn't have enough time, so we put the egg in the little cup.
Okay.
The goal was to put the egg inside the bubble wrap so that it will fall securely, so it won't break. But I tried to do something real quick.
All right, you guys ready?
Last shot.
All right, okay, here we go.
Oh my goodness.
All right, let's see how this goes.
Is there a kitchen sink on this?
All right. You guys ready? In 3, 2, 1.
Oh, sounded good. I don't know where the egg is.
Right here.
Ah.
Hold on. I'm gonna crack it.
I know, I think that's intact.
It cracked.
Nope, it survived.
Now, do you want to? Now, with this, Ian, do you have any idea how this made it?
Well, so basically, I mean, the egg started with a lot of potential energy, way up high, right? And all of that potential energy got converted to kinetic energy, and that kinetic energy had to be absorbed by something, possibly the egg. And here they have all kinds of bubble wrap and cotton balls and coffee filters.
And try to put it on.
Oh yeah.
Okay.
So
it didn't work out.
Yep.
So we put it on the side.
yeah. So a lot of different things to help absorb that energy.
Okay,
That
so
doesn't go to the egg.
all right, so you guys, good job. Go over here. Who's next?
I think they're challenging you.
Okay, where's the egg in this? Okay, all right. Why don't you tell us what your thought process was?
Our thought process was to make something that would cushion the blow so it wouldn't crack.
Okay, and what have you used here? You've got a lot of
We
stuff.
use a lot of fluff balls, and we use like these coffee grinders or something.
Filters.
Filters to make it like a parachute.
Okay, well, let's see if this parachute works.
Whoa.
Let's.
Parachutes
got a
are
little
tricky.
tangled. All right. Okay. This would not be good, this tangled, would it, Ian?
No.
All right. Okay. All right, you guys ready? Yep. Okay.
Fingers crossed.
Okay, here we go.
All right, let's see. All right, in 3, 2, 1.
Oh. Sounded pretty quiet, right? I didn't hear anything break.
Okay. Okay.
Good.
Yeah, I'm going to break it before trying to get it out.
Be extra careful.
I think it's intact.
Yeah, it looks pretty good.
Wow.
Yeah. And again, they've got like springs down here.
Yeah,
So
I don't know that the parachutes really slowed it down as much as you had hoped, but I like the little pipe cleaner springs that you had to help absorb some of the energy as well.
Good job, guys. All right. All right. Okay.
We got more?
Yeah, we've got one more. Okay, gentlemen. Describe your thought process here.
Okay. We thought that we could make it look like a rocket and have springs right here. So like it wouldn't have that much as a fall, so it wouldn't like break. And we could have a parachute so it could like sail down like kind of gently. Like, cause if we didn't have a parachute, it would just like splat.
Okay, well, let's see how well their parachute.
Yeah.
Yep, let's see. Okay.
You ready?
Okay, you ready?
All right, here we go. In 3, 2, 1.
Oh!
Uh-oh. Well, we got one scrambler here. I don't. Okay, now, Ian, sometimes these things don't work out.
Nope, not every time. But, I mean, the only failure is when you don't learn from your mistakes.
Right. And so what do you guys think you do next time to make this work a little bit better? Go ahead and speak into the. Put a little more protection on it? Yeah, it's probably not a bad idea, but good try. I mean, you did try the parachute. All right.
Overall, excellent job.
Excellent job, gentlemen. Okay, I'm going to hold on to this because we're going to get rid of this. Are you ready for some questions?
Sure.
Okay, so let's take an online question. How did engineers come up with the idea of the structure of a spacecraft?
They got to be very creative, but a lot of times the structure and the shape of the spacecraft is really driven by what the spacecraft has to do, some particular job. So for example, the space shuttle, right? That was a spacecraft that needed to generate lift so we could fly like an airplane. So the shape needed to be something like an airplane. Needed to have wings. Those wings needed to have a particular geometry so the airplane could fly very fast, so the space shuttle could enter the atmosphere very fast. It also had to have control surfaces that allowed it to maneuver through the atmosphere. Because when the space shuttle enters the atmosphere, it enters at a very high angle relative to the wind. And so it can use that nice, smooth, flat, enormous underbelly to help create drag to slow it down.
Okay, we've got one in the audience.
Where was the first airbag tested?
Where was the first airbag tested, like
Oh, goodness.
these guys?
Oh, well, so the airbags that we used for the Mars landers, the first ones were for the Mars Pathfinder mission in the early, mid-1990s. We did some tests of those out at JPL, out at the company that built those airbags, ILC Dover, and also out at Plumbrook Station, a giant vacuum chamber that NASA has in Ohio.
And they worked out pretty well.
They did incredibly well.
All right, we have another audience question.
About how long does it take to build a spacecraft?
How long does it take to build a spacecraft? It depends on the size of the spacecraft, right? The space shuttle was being designed and developed at the beginning back in the late 1960s and designed for the entire decade of the 1970s, and we didn't actually get to send it into space until 1981. Some of the spacecraft that we send to Mars may take 5 to 10 years to design, build, test, and ultimately send to Mars.
So it depends on what the job is.
It depends on the job. It depends on how big the spacecraft is. Yeah.
Yeah, okay. Let's take an online question. Do you ever use more than one parachute at a time?
Absolutely. Sometimes you need to create so much drag that the parachute to create it would just be too big to manage, right? The Apollo spacecraft, for example, that returned humans from the moon, that used a combination of parachutes, but the main parachutes had 3 enormous parachutes that were in a giant cluster to help bring that spacecraft to the right slow enough conditions before it could land in the ocean.
Okay, now next month we've been talking about the space shuttle. We will have an astronaut who actually flew on the space shuttle.
Very cool.
You send experiments out. She was actually an experiment herself.
Human guinea pigs.
Human guinea pigs. So why don't we check this out? Look at this. This is Mercury Friendship 7. This is the capsule that John Glenn flew to become the first American astronaut to orbit the Earth. Now, inside this capsule, there are these little tiny eye charts. Why eye charts? Well, doctors at the time didn't know how microgravity was going to affect the body, and they thought John Glenn's eyes might get out of shape, affecting his vision, and he couldn't be able to see the control panel. So they tested his eyes during the flight. Have you ever wondered what kind of experiments astronauts run in space? If you have, be sure to check out the next STEM in 30.
I think my big takeaway from that is how important failure actually is.
Absolutely. You got to be able to learn from failure, be able to learn from the mistakes, and take that knowledge and make corrections and come up with a better overall system at the end.
Awesome. Ian, thank you so much for joining us today.
Thanks for having me. It's been great.
I'd also like to thank our sponsor, NASA, for sponsoring this show, as well as Bill Airy from ILC Dover for bringing the giant Mars airbags along. We're going to leave you today with the sights of Roswell, New Mexico, and Goddard's lab, as well as the ranch where he launched from. And then stick around after the credits for an extended interview with Bill Siders at the Roswell Museum and Art Center in Goddard's lab. Thanks for watching.